Could you, I presume you guys can hear me, hopefully. So I'm gonna now share my screen, and then can you all can you all see my screen? Okay. Just stop me if there's any problems. It's great to be here. I apologize I could not be here in person. Um, I'm very happy to give this talk on some of my recent work on when less is more, optimizing prescription alerts under fatigue. This is joint work with Jose Empiri, who is an assistant professor at the Haskayne School of Business at University of Calgary. So first, I'm going to briefly talk about the research motivation, do some literature review, and then we're going to dive deep into the model and our case study. So what is the motivation behind the study, right? So um, how do pharmacists work? So in the United States and many other countries, pharmacists work by essentially serving as the last layer of defense between your doctors and the patient. So pharmacists are intended to check what kind of errors are in the doctor's prescription before sending it out to patients. So during our interviews, for example, one of the things that we had discovered is that the pharmacist, would call the doctor and say, "Did you mean to say 800 tablets of vitamin D per meal?" And of course, the answer is no, right? Unless the pharmacist really wanted the patient to eat vitamin D for cereal. What he actually meant was 800 international units, or one tablet for short. And so pharmacists play a very important job in the entire sort of healthcare workflow by helping to sort of stop any errors in the process before it's administered to the patient. And just to give a sense of how important this job is, on average, about 3% of prescriptions from the doctors have an error, right? And that's a very high amount because in the United States alone, on average, this leads to about 50,000 deaths due to prescription errors. And that will be one of the leading cause of deaths in the United States if it is counted as a cause of death. And so this is a big problem because prescriptions have so many errors and pharmacists have a very important job that, people have come up with a way to sort of help pharmacists, in this process. And one of the ways that we have came up to sort of help pharmacists in this process is to develop something called CPOE systems. These are called computer provider order entry systems, and they're essentially digital or computerized systems that helps the pharmacist to recognize what kind of errors in the prescriptions can be. So on the left here, we see a particular type of prescription ordering CPOE systems. On the right here, you see a different, more modern type of CPOE system that also separates the alerts into tiers. So essentially what these CPOE systems do is that they show you alerts of different kinds, whether it's because of drug-drug interaction or because a drug is ordered at the wrong dose or etc. And they basically show you, what kind of errors they have. And the pharmacists are legally required in many states and generally just sort of, operation required to go through all of these alerts to help reduce the chance of a prescription error. And these systems have helped in general. Since the introduction of these systems in the United States, Canada, and UK, there's been a lot of randomized clinical trials studies that talks about how effective these systems are. On average, they cause probably a reduction of the total error rate by the pharmacist. So total missed error rate of the pharmacist reduced them by about 50%. So it's a good thing. This is a good system, good innovation that's been integrated into our healthcare system. But there's a question of how much of of a good thing is too much. Because as people realize that it's a good thing to sort of alert to the pharmacist on what kind of things might be a prescription error, the number of errors that a pharmacist see per prescription has increased. Now, on average, the pharmacist actually see between 7 to 15 amount of alerts per prescription. And that means on average, they're dealing with over 100 to 1,000 alerts per shift, each pharmacist. That translates to over 90% of time of the pharmacist is just literally spent dealing with alerts. So the vast majority of the time that a pharmacist do on a day-to-day job is dealing with alerts. And what does that cause in terms of human behavior? That causes the humans to essentially ignore them, right? If you're faced with just so much stimuli that there's alert, there's alert, there's alert, there's alert, you start overriding them, you start ignoring them. And this has caused an override rate about of 96% in total. And so to just given a recent example, a hospitalized teenager received a 38x overdose of an antibiotic because the clinician and the pharmacist were advised to ignore all alerts coming out of the CPOE system. And unfortunately, the teenager died. Right? So here we're clearly seeing that even though having an alert system is a good thing on average, having too much of a good thing can actually be too much. And therefore, the goal of our research today is to really think about how we can understand the optimal alerting strategy when we consider the fact that the humans have fatigue and the humans do essentially sort of stop looking at things if you give them too many of them. So the research question is, how do we actually optimize these CPOE alerts to balance between providing essential alerts and also minimizing unnecessary assumptions? So I'm just going to give a brief literature overview that this problem in and of itself is not a new problem. There's been people studying it from a behavior dimension. There's people studying from a clinical dimension, and there's fewer people studying from, say, a more machine learning or sort of statistical, approach. And so all of these approaches have already looked at this problem, and they've recognized that this problem is significant. The behavior dimension has recognized that the amount of fatigue does reduce the compliance and do reduce the responsiveness of pharmacists with regard to alerts. The clinical dimension have come up with ways to perhaps tier the alerts to help this process. The machine learning approach has tried to think about how we might predict, low value alerts. But we're looking at it from a different angle, and we're thinking about how we might consider optimizing the entire alert system together to achieve what's called the optimal structure. And for us, to do this, we need to introduce, what we consider to be our model framework. So first question, before we introduce the actual model, I'd like to first introduce why is this problem even difficult? So this problem is difficult because of the following thing. You have an alert, a potential alert, right? So there's a drug prescription coming in, and you could potentially show this alert to the pharmacist. There's, on a very simplistic scale, there's two things you can do. You can choose to not show an alert, which is okay. But if you choose to not show alert, you're running at the risk of the patient, right? The patient might be seeing a certain risk that you might have ignored. Another version is that you actually do show the alert. But then in that case, if you do show the alert, then you're running the case of, okay, you might reduce patient risk, but now you're increasing their fatigue. And what does increasing their fatigue mean? That means that by showing them more alerts, you're reducing the effectiveness of them to deal with future alerts because you just used up their sort of their cognitive brain power. And this creates a recurring loop that sort of affect what your current decision affects the future decisions. And therefore, what we really have here is really, a sort of a framework in which we have these current decisions depending on future decisions. So to concretize this, so we're going to assume that when an alert comes in, it carries with particular risk. And the decision that we're going to do here is to choose to display this alert at different levels. So think of this as a different tiered of alerts that we were just talking about. The lowest level can be you just choose to not show the alert at all. And the higher increasing level can be basically levels that you say, okay, you can't override this, this is actually a pop-up window or et cetera. So there's basically different levels of alerts you can do in a CPOE system. And based on this different level of alerts, there's a base action probability. So that means given that this alert was alert of risk R was displayed at risk level L, what is the probability of the pharmacist who has features X that would act on this alert correctly? So this this is basically what we term as AX of R, L, and R. So here, of course, this is a very general function, right? We allow this base action probability to depend on X, L, and R arbitrarily. And we also assume that by displaying an alert at this level, you gain a certain level of fatigue because you've looked at this alert, you've spent time on it, and therefore you have gained this amount of gained this amount of fatigue. And what does this fatigue do? This fatigue essentially feeds into a state, psi of k, that then multiplicatively, depending on this linking function g of psi of k, changes your action probability. So in a way, you can see, you can think of it as a way in which that every alert that you show basically increases this psi of k, and this psi of k would then have an impact, a downstream impact on what your true action probability will be. And this, of course, creates the effect that we previously talked about in which your current decisions affects your future fatigue impact. And another way of looking at this is that this is essentially a one-state MDP in which our MDP, the state of the MDP is this unobserved quantity fatigue. Okay, before we talk about the actual sort of MDP, we first want to explain what this linking function does, g of psi. Right, so this g of psi here does this following thing. It basically links the level of fatigue to how much it actually impacts your decision. So here we're just showing two different representative curves of the fatigue function. So if your curve fatigue function looks like this, g of 1, then here in this case, the pharmacist and the clinician's performance quickly deteriorates with fatigue, but it basically, right, it quickly deteriorates, but it sort of staves off in the long run. But if your fatigue linking function looks like g of 2, then essentially that means that as you gain fatigue, the pharmacist is able to sort of still keep a very good sort of compliance with the alerts until some point in which they run out of run out of either brain power or just run out of just energy in general. Right. So here, this linking function essentially sort of encodes the performance characteristics of the human as the fatigue grows. Again, we don't make any strong assumptions on the function g other than the fact that it is decreasing over time, aka that the pharmacists do get more tired and do get more fatigued as the amount of fatigue actually grows. We do not here model any sort of fatigue recovery effects because in general, as in the pharmacists that we have that we have interviewed, they do not have breaks throughout their shifts. So this is, as we previously said, this is really a one-state MDP in which our current state psi of k, which is a pharmacist fatigue alert after processing k alert, transitions towards psi of k plus 1 after seeing an alert. And basically, this entire process is a process of them going through this process over and over again. So for general purposes, we're going to assume that we have a general fatigue transition map that allows them to transition between psi of k and psi k plus 1. That then this fatigue transition might depend on the L, which is the level of the alert you actually show, the risk of the actual alert that you show, and your current fatigue level, psi of k. So we allow the fatigue transitions to depend on any of these kind of things. But it turns out that this kind of general MDP structure, which is well known to be almost impossible to solve and analyze, can actually be reformulated in a much simpler structure. Under the assumption that we have it's a monotone and cumulative and identifiability assumptions. So these are relatively mild assumptions that I'm not going into detail. But under these relatively mild assumptions, then this general state transition MDP can always be rewritten as an additive state transition, meaning that there always exists a strictly increasing transformation such that if we redefine the unobserved fatigue state to be the function of the original state, then the new fatigue dynamic satisfies an additive stateless transition instead. And so what this really means is that even though there could be a lot of ways of how the fatigue function actually transitions, because the fatigue is really unobserved anyways, we can always model it as if the fatigue transition is additive. And this is a very strong result that allows us to simplify a lot of the technical challenges with dealing with MDPs. And the proof of this theorem essentially relies on order theory and group theory, and I will not go into detail, but it's essentially a transformation on the semi-groups of 0 to infinity. So and this technical result gives us a very practical meaning, which is that allows us to formulate this dynamical program with this restricted state. And using this restricted state, we can now formulate our decisions. Now our decisions here are to decide, right, as we previously said, how to show the level L alert, depending on epoch and the risk. Our objective is to maximize the total amount of risk avoided for K alerts. And here, what does the risk avoided for the K alerts mean? So this means the amount of risk that you have for each alert, which is a distribution, multiplied by the potentially probabilistic risk level that you're showing the alert, multiplied by the fatigue impacted action probability, right, which is conformed of two terms. The AX of L of R, which is your base accuracy, multiplied by this G of psi of K, G of psi. And this entire term, subject to the constraints that the probability that the level that you choose actually accords to the actual decision policy that you have, and the risk level of the incoming alerts follow this basically general distribution, and we're taking the expectations over both of them, and also subject to the fact that the fatigue dynamics is additive. So this is our entire formulation of the dynamic program, now with the understanding that we have we have this additive transition. And to analyze this, we will now analyze the fluid approximation of this MDP. When we're taking the number of alerts to infinity, a number of alerts into infinity in a continuous time process. And this is a valid approximation when the number of alerts that you see in an individual shift is very large. And in our particular case, the number of alerts that pharmacists see on the daily level, on a shift level, is relatively large, and therefore this approximation usually produces very low level of error. So now our decisions in this fluid approximation would be P of L of R and T, subject to the sort of the sum, the same objective, which is the risk avoided through alerts, now within time 0 to T, subject to fact that the fatigue now depends on now not just the sum, but the integral of the past decisions. So you can see here, this is exactly the same as the previous, except that instead of depending on every single discrete alert that comes in, we're now saying that our policy of deciding which level it will, depending on each alert, will come at a level of continuous time instead. So everything is just the same, except that I changed the unit of record from alert to a continuous time. And so this now, in this formulation that we have, now becomes the infinite dimensional functional optimization problem, which is quite difficult. So the first result that we have here regarding this infinite dimensional optimization problem is that we're going to first look at this sort of special case of this infinite dimensional optimization problem, in which we concentrate on the case in which we only have two levels. We have a stationary risk distribution, and our linking function of the G of psi follows an exponential linking function. Now, this exponential linking function is a proven used sort of function in psychology literature. We're just taking it adapted from psychology literature, that in general, sort of people's attention span follows an exponential curve. And under these assumptions, these further assumptions to our general fluid approximation, we're able to essentially prove the following result, which is that we can solve this optimization problem to optimality, and the optimal policy is a threshold function in which it depends on the screening index S of R, and you basically show an alert if and only if this S of R is greater than or equal to some kind of quantity. So let's look at this screening index right here. So what does this screening index depend on? It depends on the top numerator, which is your baseline expected risk avoidance without fatigue. So this is R times AX of R, right? Divided by the amount of fatigue you actually introduce per alert. So in a way, this is a pretty classical sort of risk versus sort of reward versus risk ratio, right? And our theorem says that under this sort of standard these sort of assumptions, that the policy is essentially a threshold policy based on this ratio. But one of the things here is that we have to note is that this ratio, the threshold that it depends on, is a changing quantity. This G of inverse of beta of T big T minus T, that's a changing quantity. And this threshold in particular decreases over time. So what we're saying here is that, this screening ratio threshold decreases over time as the time goes on. So what that means is that for a given alert, right, with a given risk, there's a particular threshold. If your threshold is above the line of G of inverse, then you show the alert. If it's below, then you do not show the alert. So what does that create in terms of the actual effect, which is that as this time shift goes on, you're showing more and more alerts. And the reason for this is because that essentially the effect of the fatigue over time is less and less. Because as you get closer to the end of a shift, you expect to see fewer alerts in the future, right? So what you want to do is that you want to be very careful in what kind of alerts you show at the start of shift, because they affect all of the alerts in your later shift, versus in a later shift, you already are close to the end of the shift, so might as well show all of the alerts. And so this is how sort of intuitively how the threshold works. There's some other properties that we prove that it increases with respect to the baseline acceptance, it decreases with respect to the induced fatigue, and et cetera, and et cetera. But one of the also interesting things is how this threshold actually depends on the tail risk. So what I mean by this is that we are here assuming that the risk function, the risk of alerts, follows some kind of distribution, and we're randomly sampling IID over that distribution. But in general, here that we see that with different types of distributions, even with the same mean risk, we're getting a very different screening threshold. And specifically, what we see is that basically the distributions that have a higher tail risk, condition on the same mean, gives you a higher screening threshold compared to the distributions with a lower risk. So here we see, for example, it's ordered here, right? The lowest screening threshold is for the uniform distribution, and then it goes to the exponential distribution, then the log normal distribution, and the Pareto distribution, which is a sort of increasing order of how strong their tails are. And so this really illustrates the fact of like what the screening threshold depends on in this particular case in which we only have two levels. Now, given the time limitation I have, I'm going to sort of only quickly go through the next part, in which the next part of this basically talks about comparing our optimal policy to some baseline policy figures, which includes like the all alerts policy, if we just show all alerts without thinking about their fatigue at all, or just showing no alerts at all. And basically we're able to, and then another policy that we actually compare it to is what we call the optimal fixed policy. So what the optimal fixed policy here is that basically instead of a changing threshold over time, we force the threshold to be constant. And the reason for considering this class of policies is because the pharmacists that we've worked with said that, great, you've proven that this optimal dynamic policy is optimal, but it's difficult to implement because it will mean that the same alert shown at different time in the same shift would either go to show or no show, right? It might confuse pharmacists over time because, okay, you showed this type of alert later in my shift, but not earlier in my shift. And so even though it's mathematically optimal, it might be, practically difficult. So we also consider if we can essentially approximate our optimal policy with this optimal fixed policy instead. And basically our result here to be very broad, is that the optimal fixed policy is optimal if and only if the tail of the distribution of the risk that we have is light tail, specifically meaning that the tail of the distribution belongs into the Weibo extremal value distributions or the Gumbel extremal value distributions. If instead it belongs into the Frechet class of extreme value distributions, then the optimal fixed policy is not optimal. And intuitively, this makes sense. And the reason why this makes sense is because as the amount of tail risk of your alerts become higher and higher, conditioned on the same mean, it's harder and harder for a fixed policy to essentially both accommodate the fact that if you choose too many alerts, if you show too many alerts, you'll get fatigued and still maintain sort of showing enough alerts so that you get sort of the patient benefit from it. You really need the dynamicity of the optimal strategy if you really have strong tails. Sort of essentially stronger than exponential tails is the mathematical formulation. And so we really see here that we have near optimality of optimal fixed policy if and only if we have light tails. And but what I'm going to skip this part and I'm going to skip to where we talk about our case study in which we have collaborated with the University of Alberta Hospital System. We've gotten the total number of we got their alert data from 2021 to 2024, in which we saw the number of alerts per shift, which is 142, with more than 10% of shifts having more than 450 alerts per shift, with an average override rate of 78%. And so really this again, the real data again corroborates our story that really pharmacists are seeing a lot of alerts in each of their shifts. Now I'm gonna skip through all the parts in which how we actually estimate the risk of a single alert and how do we estimate the behavior model. I'm just gonna show you the final results that we have here, in which if when we compare that our policy, both fixed and both the optimal fixed policy and optimal policy, compare with the current policy. And what we show here is that compared to the current policy, which is basically showing all alerts, we're able to reduce the number of alerts by 33%, but more importantly, we're able to reduce the number of life-threatening alerts by 40%. And this means that on average, we expect over the United States level that we would save over 2,000 to 4,000 lives every year due to this optimal dynamic policy, and over $500 million cost across the United States. And so in summary, we have developed this a novel fluid approximation model for alert decision making under operator fatigue. We proved that under this result that that how the optimal alert looks like a threshold policy, and that depends on the risk-reward ratio. We also extend our results into the general case, in which we don't make the two-level assumptions. Qualitatively, the results hold. They're just much more difficult to explain in the presentation. And finally, we showed on real-world data our impact, which is that we are able to save over 2,000 to 4,000 lives and over $500 million in cost. And with that, thank you very much. And the paper link is on here in the QR code, and I'm welcome to have any questions.
Thank you very much. Are there any questions on the audience or on the chat?
Hi, yeah, thank you for the talk. It was very nice. I didn't understand if there is when you calibrate the thresholds, does it depend
Yes.
on the particular person that's doing the clinician, or
Yes.
in general for all the people who work in a particular hospital, or how does
Yes. Yes, great question. Good question. So here we are assuming that our entire model is on the pharmacist shift level, meaning that we're assuming condition on basically conditioned on the pharmacist and the shift, then the threshold only depends on the risk reward ratio of the alerts. Now, our model allows for arbitrary sort of specifications of pharmacist shift level covariates. So let's say if you have a large hospital, you have a bunch of different pharmacists, they can have different thresholds. Absolutely. But it's just that we're modeling on a pharmacist shift level threshold to allow us to be able to sort of quantify sort of the threshold and the behavior of these policies in terms of the key variables that we're interested in. But it's a great question. Like we allow in general sort of pharmacist shift level covariance.
Thank you. And another question is the fatigue, is there an index of fatigue that could be a byproduct of this model?
Great question. So you do have to assume what fatigue model you use in the estimation of the parameters here. So we use the exponential model because it's the classical model that's been specified in psychology. Now, you might wonder if there's a way to data-drivenly estimate the fatigue model. It turns out the answer is it's difficult for that to be identifiable because you essentially don't see the fatigue state. You don't see the actual fatigue transition. You only see the effect of that fatigue transitions. And therefore, there's many functions that essentially corroborate the fatigue, the function that you have. Now, one way you can do is estimate on one set of the data and then validate on the other set in a train test splitting way. And so that's the way. That's in the future work that we're going to try to explore that. But in the current way, we are assuming a particular parametric form of the fatigue function and fitting the parameters of that parametric form. Now, whether that parametric form is correct or not, that depends on the specification of your model.
Thank you.
Great.
Dr. Li, are there also plans for implementing this? Is Alberta Hospital already thinking of implementing?
Yes. So we are definitely thinking of implementing this. So as you can imagine, implementing this and changing pharmacist behavior, changing hospital operations is not an easy process. So it definitely will take time. I don't expect this to be done anytime soon, but we are in deep discussions with not just the Albertan Hospital. In fact, that we're in deep discussions with actually CPOE providers, the system generators who actually generate those systems. Now, one of the reasons why they currently show all alerts instead of selectively showing alerts, why the CPOE systems default to showing all alerts, is a liability reason. Right? So imagine your CPOE system, you sell it to a hospital and you select what alerts to show. And then for a particular reason, alert wasn't shown and the patient died. The CPOE system can look like it has liability. If they choose to show all alerts, it looks like they have no liability. Well, in reality, they actually have liability because they're just overwhelming pharmacists with alerts, right? But it takes time to sort of change that around in terms of how people think about this. Yeah.
That's great. Thank you very much.
Yeah.
Any other questions? All right. Let's thank Dr. Li again for the amazing talk. And
thank you. Thank you all for inviting me. Thank you.
We hope that you come in 2 years to Costa Rica.
Yes, I hope that will be here in person so I can escape the cold Boston weather that I'm also not enjoying right now. So
high 80s here. So.
It's great to hear. Thank you again for the invitation.
Bye.